Okay. Thank you, Sonia. It's my honor to talk here. Right, I will share submit the paper, which titled Composites, Multiple Mode OFDM with Index Modulation. Right, I'm so happy to talk here. So can I start now?
Yes, please. Yeah.
Okay. So I will change my PPT to the full screen. Okay. Okay, so due to the large amount of mobile user, and the system capacity is nowadays is very high, right? So we can see from this figure there are 3 dimensions, and the first one is network density, and the second one is spectral efficiency, and the third one is frequency band, right? So it is very hard to meet these huge requirements, and my work is only focusing on the spectral efficiency. And okay, I go to the next slide. First, I will introduce 2 technologies in the 4G systems. And the first one is OFDM. So I think everyone is very quite familiar with this topic. In the OFDM system, the first advantage is the combating the ISI inter-symbol interference. And the second one is the Ofdm is very easy to implement. So as we can see from this figure, and all of the subcarriers are orthogonal in the OFDM system. This is quite important and to maintain the benefits. But there are still some problems for OFDM. The first one is the PAPR, and due to the Doppler shift, the orthogonality cannot be guaranteed. So the first one is CFO, right? And the second one, and the second is the ICI. And due to the CFO and the ICI, the orthogonality cannot be guaranteed. So how to solve this problem? I will talk about this topic later. And the second technology is Mimo technology. And as we can see in this figure, and in the conventional V-blast skin, and two symbols will simultaneously transmitted to the receiver. And in the unmounted space-time code, and two symbols will transmitted to the receiver during multiple time slots. There are some the advantage of the Mimo technology is about the spectral efficiency or transmitting rate. And if we increase the number of transmit antennas, and the transmit rates will be very high. But there are several disadvantages for the Mimo technologies. The first one is the interchannel interference. The second one is the synchronization. The third is the multiple RF chains, and the last is low energy efficiency, right? But I think the OFDM and the Mimo technologies are quite important for the current 4G technologies. So how about the 5G technologies, right? And I just mentioned three technologies for the 5G system, and the first is full duplex transmission, and the second is massive MIMO, and the last one is spatial modulation, which I have which is my research topic. So what is the spatial modulation? Let's see what is the spatial modulation. Actually, the spatial modulation is the variant of the Mimo technologies. So, in this figure, we can see that in the conventional Mimo scheme, all of these antennas, all of these 4 antennas will be used for transmission. But in spatial modulation, only single antenna will be used. So, for example, if we only use the first antenna, and the last 3 antenna will not be used, and there are two dimensionals. First one is signal cancellation, and the second one is spatial cancellation. So I have just said, the Lambo, the index of each antenna is the spatial cancellations. If we use the first antenna, the index will be 0, 0. If we use the fourth antenna, the index will be 1, 1, right? So this is the main difference between the spatial modulation and the Mimo system. So let's see this figure. If the X1, right, the X1 is transmitted only through the first antenna, that means the index piece is 0, right? Is 0. If the X2 is transmitted through the second antenna, the index piece will be 1. And there are 4 advantages for SM. Right, the first one is multiplexing gain is very high, and it has lower receiver complexity, and the power and it has higher power amplifier efficiency. And the last one is it has higher energy efficiency, right? Because the spatial modulation only use 1 transmit antenna, so the power consumption is very, very low compared to the Mimo technologies. Let's see one example, right? It's very clear here. If we want to transmit the 101, well, it's 101. The first 2 bits, 1, 0, or here, this is better. The 1, 0 means we will use the second antenna here, right? The 1, 0. 1, 0 means we will use the second antenna to transmit the modulated signal. But the index is 2, right? From 0, 1, 2, and the last bit is 1. In the BPSK constellation means the -1, right? So we have the antenna index 2, the third antenna, and the transmitter transmitting -1. So the whole the Intel transmit vector is like this form: 0, 0, -1, and 0. So only the third antenna is used, and the other antennas are not used. So from this transmitted vector, we can clearly see the difference between the spatial modulation and the Mimo technology. But actually, right, this transmitting rate or the length of the index piece is considerably lower than the conventional Mimo technology. But the BR performance will be better than the Mimo technology. And this is the channel model of spatial modulation. This is the same signal vector, right? 0, 0, and -1, 0, and there is only one receiver antenna and 4 transmitted antennas. So in this case, only this channel will be used, right? If we multiply the channel matrix, and the signal vector, we will get the minus H2 plus N, right? So actually the receiver side will only receive the minus H2 plus some noise. If the SNR is high enough, right, it is only minus H2. So the detection for the spectral modulation is very simple. It just only considers which channel will be used, and only has the minus, only has the sign plus and minus. So compared to the Mimo technology, right, the complexity is largely reduced. Yes, this is the ML detection for the spectral modulation. The Y is the receiver antenna, and the H is the channel matrix. The S, right? The S is the all possible candidates for this for the transmitted vector. So we just change this S from the first to the last of all transmitted candidates. Then we will find one selected transmitted vector with the minimum Euclidean distance, right? This is the classic ML detection rule. But the complexity is still very high if the transmitted antenna is very large, right? If the n is equals to 64, right? The complexity is still very high. Okay, this is the simulation results of SM. So from this figure, we can see that the SM has the best VR performance than the conventional V-Blast, right? This is the conventional Mimo skin and the MRC. But from this legend, we can see that the SM has the four transmit antennas, and the V-Blast has only 3 transmit antennas, and the MRC skin has only 1 transmit antennas. So the SM obtains the better performance, but with the most transmit antennas, right? This is kind of trade-off scheme compared to the Mimo technologies. Okay, this is another variant spatial modulation scheme we called Quadrature spatial modulation. So in the conventional spatial modulation, the transmitted signal will be directly sent to the receiver, but in the QSM scheme, the transmitted signal will be split into the 2-dimensional, right? This is the real part. Now this is the imaginary part. Okay, we can see this figure is much better, right? So the transmitted signal X is split into the XR, the real part, and the XI, imaginary part. So the index space, right? There are 2 index space. The first one is to control the index for the XR, and the second one is to control the index space for XI. So for example, if we have 1 and 0, the first one means the XR will be transmitted through the second antenna, right? If we only have 2 transmit antennas, the 1 means the XR will be transmitted through the second antenna. The 0 means the imaginary part will be transmitted through the first antenna. So if we have the 0, means the first antenna will transmit the real part and the imaginary part. So the length of the information bits, or the transmission rate of the QSM is the log2 NT, right? The log2 NT means the index selection for the real part. Another log2 NT is the index selection for the imaginary part, and the log m, right? Log m is just the modulation bits for x. But for the conventional SM, right, there is only one log2 NT here, which means the modulated signal x will be directly transmitted through only one antenna, right? So compared to the SM, we can see that the QSM will have a larger transmit rate, right? There is the additional log2 NT here. Okay, the spectral modulation and the quadrature spectral modulation, and all of these schemes are the Mimo relevant technologies. But is there any OFDM relevant 5G technologies? Right, we have introduced the Mimo technology and the OFDM technology in the first two slides. So the SM and the QSM belongs to the Mimo relevant technology. Then we will still see the OFDM relevant 5G technologies, which is OFDM with index modulation, right, which is quite similar to the spectral modulation. Okay, this is the concept of index modulation for the OFDM systems. And this figure is the conventional OFDM system. And in the conventional OFDM system, all of the subcarriers will be used for the signal transmission. Right here has like the 16 subcarriers. All of these subcarriers will be used. But for the OFDM IM systems, only some parts, only the partial subcarriers will be used. For example, if we see this one, only 15 subcarriers will be active, right? The M means N is equal to 1. The N means the number of inactive subcarriers. Only one subcarrier is not used. If we see the last figure, two subcarriers will not be used, right? Also, we can say that we can set M equals to 3, right? Then only one subcarrier is active. So compared to the conventional OFDM, the OFDM IM scheme is more flexible, and it has much better BER performance than the OFDM. So the reason is not all subcarriers. Not all subcarriers are used compared to the OFDM. Then, at the receiver side, it is quite easy to detect the number of subcarriers, the pattern, the active pattern of the subcarriers, and also the modulation symbols, right? For the OFDM, for the conventional OFDM, and the receiver will check all of the subcarriers, which symbol will be transmitted through the first one, the second one, until the last one. But for the OFDM IM, right, it will not be that complex. It only needs to detect these two subcarriers, right? The first two, or the last two, or the second and the last, which means the complexity, the detection complexity of the IM will be largely reduced we will see this detection methods later. Okay, this is the specification of the Ofdm IM and the classic Ofdm. And the first one, I haven't mentioned that, right? And the first one is PAPR problem, and due to the partial active subcarriers, the Ofdm IM will have reduced PAPR. And the second one is the BR performance, right? And the Ofdm IM will have the better BR performance than the conventional OFDM. And the third one is the complexity. Compared to the OFDM, compared to the classic OFDM, and the Ofdm IM will have similar complexity. But if the number of subcarriers is very large, right, the Ofdm will have the lower complexity than the conventional Ofdm. And the last one is the efficiency. And in my opinion, the Ofdm IM will have the somehow smaller spectral efficiency than the Ofdm. And this is also one open problem. Many people have published some papers to improve and the spectral efficiency of Ofdm IM, right? But nowadays it is very hard to approach the same spectral efficiency to the Ofdm, but with only the smaller gap. Okay, and this is the spectral efficiency of Ofdm IM. Let's see this. And the first part, right? The first part is the index space for selecting the subcarrier pattern, right? If we have the L and M, the M means the number of inactive subcarriers, and the L is the total number of subcarriers. So the compilation of selecting M subcarriers among L subcarriers, the number of is the CL dot M, right? This is the number of all of the compilations. And the L minus one and the L minus one subcarriers are active. So that means the index space of transmitting modulation symbols is L minus one log 2M. So if the M is equal to 0, if the M is equal to 0, and the L multiply L log 2M, this is the exact spectral efficiency of classic OFDM. And this is why I have said the OFDM IM it is very hard to achieve the same spectral efficiency of the Ofdm IM, and that means it is very hard to set the M equals to 0, right? If the M is 0, then it is the conventional Ofdm scheme. But if the M is greater than 0, the spectral efficiency of IM is always less than the classic Ofdm. So what is the benefit compared to the Ofdm IM? I will first show you the simulation results. So from this figure, we can see that the Ofdm IM has better BR performance than Ofdm, right? The purple line, is better than the black line, and the BR of 10 minus 5, it will have 3 dB, almost 3 dB SNR gain. right? This is because in the high SNR region, and the detection of subcarrier pattern will not be wrongly detected. The modulation error, the detection error only comes from the modulation symbol, right? So in the conventional Ofdm scheme, all of subcarriers will be active for transmitting modulation symbols. But for Ofdm, IM, right, only partial modulation symbols will be transmitted and detected. So the BR performance of the IM will certainly better than the conventional Ofdm. Okay, this is another variant of Ofdm, IM, which is Ofdm with IQIM. The Ofdm IQIM is quite similar to the previous QSM scheme, right? The idea of the Ofdm IQIM is to split the transmitted symbol to the in-phase part, right? We also call this as the real part and the imaginary part, right? So from this figure, the real part and the imaginary part of the transmitted symbol will be split, and then the real part will select its own subcarrier pattern for the active subcarriers, and the imaginary part, right, will select another subcarrier pattern, right, and similar to the QSM scheme, and the same signal, right, the same transmitted signal, but with 2 times of the subcarrier selection. So of course, the Ofdm IM IQ will have a better spectral efficiency than the conventional Ofdm IM. Okay, here, right, and the blue line and the green line has a better performance than the purple line and the black line, right? And that means the Ofdm IQIM will have the better performance than the Ofdm IM and the Ofdm, and the BR of 10 to the power minus 5, and it has almost 6 dB gain than the conventional Ofdm, and it has almost 3 dB gain compared to the Ofdm IM. And this is because the Ofdm IQIM selects 2 times of subcarriers, right? So in the high SNR, the smaller how to say, the antenna subcarriers, the subcarrier active pattern will not be wrongly detected for the Ofdm IQ, and it has the larger length of the index space compared to the Ofdm IM. So in the high SNR, the Ofdm IM will of course get the better performance than the Ofdm IM, and the spectral efficiency for these schemes are 2 bps per hertz, right? Okay, this is another mode for the Ofdm IM, which is called multiple mode Ofdm IM. And as we know that in the conventional Ofdm IM scheme, not all subcarriers are active, right? Some subcarriers will not be used. So can we use all of the subcarriers to transmit more modulated symbols, and also with the index of all subcarriers. This is the multiple mode Ofdm IM, and the index space is not based on the selection of all subcarriers. The index space comes from the constellation pattern of all subcarriers. It is better to see the next slide here. Here, right? For example, this is quite small, right? For example, if we have n subcarriers, this is small n, and all of subcarriers will transmit one modulated symbol. For example, the first subcarrier will transmit x1. The second subcarrier will transmit x2, and the last subcarrier will transmit xn. But the difference is, from compared to the Ofdm, the difference of the of the IM is that the will select the different constellations or distinguishable constellations, or we can say rotated constellations. So let's come back to this slide. This is the first subcarrier, right? The first subcarrier in the conventional Ofdm, it only has the BPSK. This is conventional BPSK constellation. But for the Ofdm IM, it has the conventional BPSK and the rotated BPSK constellation. Similarly, for the second transmitter antenna, the Ofdm in the conventional Ofdm, this subcarrier can only transmit the signal from the conventional constellation, but for the of the IM, right, it can transmit signal either from the conventional BPSK or the rotated BPSK. So if we see the whole subcarriers, the BPSK and the rotated BPSK will have a constellation pattern, right? If we define this constellation is x1, and if and the rotated constellation is x2, so we can have a rule, right? We can have a rule that the first constellation, the first subcarrier will transmit it x1 or x2, which comes here, right? The x1, this is the capital X, right? Like the chi, and the x1, x2, or we transmitted x2 and x1. This is an index space for the permutation of the constellation of the different constellations. For example, here we have x1 or x2. In the other case, the first subcarrier can transmit the signal from x2, and the second antenna can transmit it from the signal in x1. So we call this one is the permutation pattern. This one is another permutation pattern, and we give the index space for these two patterns, right? This is 1, this is 0, this is 1. So compared to the Ofdm IM, in the Ofdm IM, all of the subcarriers will be used but the difference is the constellation selection. X1 is the conventional BPSK. The X2 is the rotated BPSK. Sorry, how to erase? Okay. This is X1, right? This is X1. This is X2. So how to transmit it, the signal from X1, X2? That is the key point for the multiple mode Ofdm IM. Right? Okay, it has already cancelled here, right here. Then so we just keep in mind that the permutation of constellations will give the index space in the MM or Ofdm IM system. Okay, this is the spectral efficiency of MM. The log 2m, the log 2n factorial. This is the Lambo. This is the Lambo of all or the combination of permutation, the constellation permutation, right? If the n is 3, then we have 6 kinds of constellation permutations. It's like 1, 2, 0 or 1, 1, 2, 3, 1, 3, 2, and 2, 2, 3, 2, 3, 1. It has 6 compilations of the permutations. So the spectral, so the index space for the MM is log 2n factorial, and the here is n multiply log 2m. That means n subcarriers will transmit n modulated symbols, and the upper part is the transmission bits, and divided by n, that is the spectral efficiency. So from this part, we can see that compared to the conventional Ofdm scheme, right? Then the first two parts are the increment or the increase of the spectral efficiency compared to the classic Ofdm. So from this equation, we will see that the BR performance of the MM Ofdm IM will be better than the conventional Ofdm. This is another variant scheme of Ofdm IM. We call it the composite multiple mode Ofdm IM. This is my recent work. I have just submitted this work to the IEEE transaction on wireless communications. But I have just submitted two months ago. Okay, the motivation of the composite multiple mode of the IM is that in the Ofdm IM, right, not all subcarriers are active. In the multiple mode of the IM, all subcarriers are active. So can we combine these two schemes of Ofdm IM and the multiple mode Ofdm IM? So and we can also consider another dimension, which is called the power dimension. Here, right, I have mentioned allocate the different power to the active subcarriers. So for example, if we activate the first and the third and the fourth subcarriers. Can we allocate the different power to these three subcarriers? So I just give the coefficient, the energy coefficient L1, L2 until the Lk to this active subcarriers. And there's one constraint, right? There's one constraint. We should have the total energy I. This is the capital I. For example, if I equals to 4, if the I equals to 4, then and the L1 plus L2 plus Lk should be equal to 4, right? If the I equals to 4, and this is the constraint for the total energy. Why should we add this constraint? Because for the Ofdm Im, the mm over the Im, we should give the same power coefficient to the different constellations. Then we can compare the system performance, which one is better, which one is worse. Okay, it is clear to see our difference from the conventional Ofdm Im and mm Ofdm Im. So in the conventional Ofdm Im, right, the index bit selection exists, right? The P1 bits, it has P1 bits and it has P4 bits. So in the conventional Ofdm Im, it only has the first part and the last part. In the multiple mode, of Ofdm Im, it has only the mode selection, right? The P3 bits and the P4 bits mode selection and the modulation bits. And there's another conventional scheme, which is called Ofdm index composite modulation. It has only the first part, P1 bits and the P2 bits and the P4 bits. So in our scheme, I integrated all of the four conventional scheme into the one part. So in the composite multiple mode Im scheme, it has 4 parts. The first part, P1 bits, are used to select the active subcarrier pattern, and the P2 bits are used to select the energy allocation pattern, and the P3 bits are used to select constellation permutations, and the last bits, P4 bits, are used to generate the modulated symbols. The spectral efficiency of the composite multiple mode index simulation is given here, right? I have just said this is used for P1 bits. If we have the total number of subcarriers n and the partial active subcarriers k, then the P1 bits is equal to the compilation of the k subcarriers among all n subcarriers. And this one, the I-1 and the compilation, of I-1 and the k-1 is the number of composite bits. That means it has different energy allocation pattern for the total energy I, right? The computations, the number of compilation is I, the C I minus 1, K minus 1. And this one, this is the number of constellation multiple modes. We call mode base. This is the number of different constellation permutations. And the last one is the number of modulation bits, right? So the K subcarriers will transmit K modulation symbols. So the modulation bits is equal to K multiply log 2m. Here, this is the conventional index composite modulation scheme. So in this scheme, so the only difference between these two equations is this log 2 K factorial. That means in our scheme, in the conventional multiple mode scheme, we consider the modulation, consider the multiple mode concept into the conventional composite modulation. So we can conclude that the conventional Ofdm index composite modulation scheme, right, ICM scheme, does not consider the multiple mode concept, right? So the increase of the spectral efficiency is not that high. And another key point is that the distinguishable or the rotated constellation sets is larger than K, right? In the modulation in the multiple mode of the IM, the number of different constellation sets is K, right? We have said this is K, but actually sometimes it may be higher than K. Maybe we have Q distinguished constellation sets, which is larger than K. Then in that case, the composite multiple mode of the IM will have much higher spectral efficiency than the conventional multiple mode index modulation or conventional composite modulation scheme. Okay, let's see the mapping table. The mapping table of the composite of the IM. So there are 4 parts, right? There are 4 parts. The subcarrier activation pattern. This is P1 base, and the energy activation pattern, energy allocation pattern. This is P2 base, and the constellation allocation pattern or the constellation commutation pattern. This is 3 base, and the last one is the transmitted vector. So, for example, if we have n equals to 4 and the k is equal to 3 and the I is equal to 4, then we have 4 kinds of different subcarrier pattern, right? And the 1, 2, 3 means the first subcarrier, the second subcarrier, and the third subcarrier are used. The 3, 2, 3, 4 means the second subcarrier, the third subcarrier, and the fourth subcarrier are used, right? There are totally 4 kinds of different subcarrier activation patterns. For the energy activation pattern, right? Because the I is equal to 4, that means the energy or the power allocation pattern to these 3 subcarriers will be equal to 4, right? The 1, 1, 2 means the first subcarrier have the 4/1 energy, 4/1 energy, right? The total subcarrier is 4, and this one has only 1/4 energy or power, and the second subcarrier will still have 4/1, sorry, 4/1 energy, power, and the last, the third subcarrier will have 2/4, 4/2 power or energy, right? I have mentioned here, right? This is 4/1, and of course we will add the square, right? And this is power factor or the power coefficient. This is square 4/1, right? This is square 4/1, square 4/1, square 4/2, and for the first one and the S1 is the BPSK subcarrier S1. The S2 is the rotated BPSK constellation. The S1 is the conventional BPSK constellation. S2 is the rotated BPSK constellation. S3 is another rotated BPSK constellation. So that finally, if we choose the subcarrier pattern 1, 2, 3, if we choose the energy allocation pattern 1, 1, 2, and if we choose the constellation permutations S1, S2, and S3, then finally we will get this transmitted vector, right? How to say, the square, right? 4/1 S1, square 4/1 S2, and square 4/2 S1, and the last one is 0, right? Because the fourth subcarrier is not used. This is the Intel mapping table, and for the N4 for the 4 subcarriers and the 3 active subcarriers and the total energy 4, right? So let's see one specific examples. These are 3 distinguishable constellations, right? And this is the conventional BPSK constellation S1. S2 is the rotated 40 degree rotated BPSK constellation, and this is the 90 degree rotated BPSK constellations, right? And those 3 constellations are independent and distinguishable. If the information base are 1, 0 and 0, 0, 0, 0, 1, 0, 1, then we can split this information base as 4 parts, right? The first part is the index base 1, 0, 1, 0, right? Because we have 4 subcarrier activation pattern. Then we have 2 bits. The 1, 0 means we will choose the 1, 3, 4, the first, the third, and the fourth subcarriers as the active subcarriers, right? The 1, 2, 3. So the 1, 0 means 3 means the third subcarrier pattern. So so we have 1, 3, 4. This is the active subcarrier. This is subcarrier activation pattern. Okay, the third one is 0, right? The third one is 0. That means the composition bit we will choose the first. We will choose the first energy activation pattern. First one, right? This is selected. Then the first one is 1, 1, 2. 112 means the energy allocation pattern is a square of 4/1, a square of 4/1, and a square of 4/2 for these 3 active subcarriers. And these 2 bits 0, 0 means the mod bits, right? The constellation permutation pattern is here, right? The 0, 0, 0 means the first one. The S1, S2, and the S3 means 1, 2, 3, right? S1 is here, S2 is here, S3 is here, right? And the last 3 bits, 1, 0, 1, means the first one, the first bit 1 will be selected from the S1 here, S1. The 1 means the -1, right? The 1 means the -1. So the transmitted symbol and the first subcarrier is -1. The -1 is for the first subcarrier from the S1, the S1 constellations. Okay, the second is 0, right? The 0 means the second symbol from the S2. This is the second symbol. So we just write here 2 here, right? It's the same. I just drag this constellation here. And the last one, oh, sorry, 0 is the first one, right? The 0 means the first one. So we just write here, right? The minus and 2/√2 plus 2/√2 j, right? The first one is here. 0 means the first one. The 1 means the second one. So similarly, the last bit 1 means the second bit from the S3. So it's plus j here, right? The plus j here. So this is plus j. So if we combine all of these vectors, then we will get finally we will get the transmitted signal vector x is in this form, right? Is in this form. First subcarrier is active, right? First subcarrier is active, transmitted the plus the 1 and multiply this energy coefficient, right? So the square 4/1 and multiply 1. So we still have a square 4/1. The second subcarrier is not used, right? 1, 3, 4. So the second subcarrier is 0. Third subcarrier is this one, right? This is the third subcarrier, and the multiply is corresponding energy coefficient or power coefficient square 4/1. Then we will have this form. This is the transmitted symbol at the third subcarrier. So similarly, the last one is the plus j multiply square 4/2, right? So we will have square 4/2 j. So finally we will have this, right? This one is similar as this form, right? If we add the E1 here, E2 here, and the S1, S2, S3, then we will finally get the same form, right? This is the final this is the finally transmitted vector. Okay, this is the ML detection, right? This is the ML detection for the composite multiple modes of the IM. Similarly, the X1, the XF, right? We read the XF. It's just the transmitted vector here, right? This is the XF actually. So if we have the x is the diagonal of the vector s, then we multiply the channel coefficient, the matrix of the transmit signal and the noise plus noise. Then finally we will get the y. Y is the receive signal at the receiver side. Since it is the Ofdm system, so so this operation is same as the dot multiplication, right? The first one, the first symbol multiply the first step of the channel coefficient. The second symbol multiplies the second channel coefficient, and the last one multiply the last symbol multiply the last channel coefficient. So that is why we should write like this: the matrix is multiplied by the channel vector, right? And this is the difference from the Ofdm system and the Mimo system. Okay, if we get the y, then we should use the same method, right? We should change change the order of the candidates of the possible vectors, just like this one, right? We should consider all of these possible transmitted vectors, and put all of the transmitted vectors one by one here. Then we will get the minimum Euclidean distance from only one transmitted vector. If we just try this transmitted vector into the ML equation, then we will get the minimum Euclidean distance. If the x is not in this form, right? If the x is not in this form, then the Euclidean distance will be larger than the smallest. So if we have the x, right? If we correct it, get the transmit signal vector x, then we will get the s. What is s? What is the estimated energy allocation pattern, and the permutation, and the index. This is the index activation pattern. This is the energy activation pattern, and this is the constellation permutation pattern. Then all of this pattern will get the final index, the information bits, right? This is like the reverse process for obtaining the information bits. If we have x, if we have the estimated x, right? If we have the x, then we will get the inverse process to have this information bits. Similarly, right? If the number of subcarriers is very high, if the modulation order is very high, if the total energy is also very large, and also if the constellation, its number of constellations is very large, then the detection complexity for the composite multiple mode will still be very, very high, right? This is common problem for the maximum likelihood for the ML criteria, right? For the ML detection. So how to reduce how to reduce the complexity of the ML detection. Then we proposed. Okay, we have already seen this, right? Then we proposed here. Okay, sorry. Let's first see the performance comparison of the composite multiple mode index modulation. From this figure, we can see that the composite multiple mode index modulation has the very big performance improvement compared to the conventional composite modulation scheme and the conventional index modulation, right? And we can see here it has almost 5 dB gain, 5 SNR gain compared to the Ofdm IM, and it still has almost 3 SNR gain than the conventional ICM, right? So we can conclude that the composite Ofdm IM has the better performance than the conventional FDM IM and Ofdm ICM. And actually there is another curve, but I didn't add in this PPT. The Ofdm, the composite multiple mode IM will have better performance than the conventional multiple mode IM. Maybe it's here, right? But I didn't add in this performance simulation. So let's see another. This is QAM. This is n equals to 4, and using QAM, right? We can still see that the composite multiple IM, it's better than the conventional ICM scheme and the conventional Ofdm IM scheme, right? Even the transmission rate or the spectral efficiency is very high, but it still has the better performance around like 2.5 dB performance gain and the 1 dB performance gain than the conventional Ofdm IM and the conventional Ofdm ICM. Okay, if we keep increasing the number of subcarriers, if the n equals to 8, right? N is equal to 8, then the SNR of 45, right? This is very high SNR, and then the composite multiple mode composite IM still has the better performance than this two conventional scheme. But in the low SNR region, right? In the low SNR region, the composite IM is worse than this two conventional scheme. The reason is that in the low SNR region, the active the subcarrier activation pattern, the power allocation pattern, and the constellation permutation pattern are very easy to get the error. So in the low SNR region, and the BER performance of composite multiple mode IM is worse than this two scheme. But in the high SNR region, the performance error only comes from the modulation bits, right? In the composite multiple mode IM, it has BPSK, right? There's BPSK constellation. But for the ICM and the IM and the conventional IM, and they use the QPSK and the 8PSK, right? So in the high SNR region, the BPSK is obviously better than QPSK and the 8PSK. So in the high SNR region, so in our paper's conclusion, we also said that in the high SNR region, the composite multiple mode IM obtains the better performance than the conventional schemes. But in the low SN region, we haven't found the methods to solve these problems, and this is also one open problems for the spectral efficiency improvements. Okay, this is our second work. This is our second work about the IQ extension, right? This is same as the QSM, the quadrature spatial modulation, and is similar to the Ofdm IQIM, right? The key point of the composite IQ is that we have still divided, we have still split the transmission bits into two parts, right? One is PI bits. While the PI bits are used to transmit the real part of the transmitted signals. Those are the real part of the transmit signal will still have the subcarrier pattern, right? The index selection, the energy allocation pattern, the constellation permutation pattern, or the modulation scheme. This is for the real part, and then there are three the index. Still, we still have this three index. Similarly, for the imaginary part of the transmit signal SQ, right? It still has these three parts: the index selection, the subcarrier, active subcarrier selection, the allocation pattern selection, and the constellation permutation selection, right? So this one, we can say this one is a small part of composite multiple IM. This is another part of composite multiple mode IM. Then if we combine these two parts, the spectral efficiency of the composite IM IQ will be still better than the composite multiple mode IM. Right? Let's see the comparison of the spectral efficiencies. So the first one is the spectral efficiency of composite multiple mode IM, right? Those two parts, we have already knew the contents of these four parts, and the second one is the spectral efficiency of the composite multiple mode IQ. So we can see here, right? The index bits is 2 times larger, and the index bits of the IQ is 2 times larger than the conventional composite multiple mode IM. Similarly, the composition bits, right? Composition bits for selecting the energy allocation pattern. The number of the composition bits is also 2 times than the composition MM. Similarly, the modulation bits are the mod bits for selecting the constellation permutation pattern. Right, the number of this is still 2 times than the composite multiple mode. The last part are same, right? The MI and the MQ should be equal to the M, right? This means if we have the QAM constellation, then this is the real part. This is the real part. This is the imaginary part. So those parts are same, but the first three parts are different. So if the number of subcarriers is large enough, if the total energy is large enough, then the composite multiple mode IQIM is able to get the 2 times higher. It's able to get the 2 times higher spectral efficiency than the conventional composite multiple mode IM. Right. Obviously, this is the benefit of the IQ concept. It's the benefit of the quadrature spatial modulation concept. But the complexity of the composite multiple mode IQ will be very, very large, right? Because we have to select the subcarrier index, subcarrier activation pattern 2 times. We have to select the energy activation pattern 2 times. Also, we have to select the constellation permutation pattern 2 times. So the complexity is considerably higher than the composite multiple mode, but with the better performance. So it is also the one kind of trade-off scheme of the composite multiple mode IM. Okay, this is the performance comparison of the composite multiple mode IQ IM. So in this scheme, so in this figure, we can see that the composite multiple mode IQ scheme has a huge performance gap, right? This one, the blue line, and the green line, right? The performance gap between these 2 lines is very large, right? It's almost 6 dB SNR gain. And another, right? The purple line has almost 10 performance gain compared to the conventional composite multiple mode IM, right? So we can conclude that this big performance comes from the sacrifice of the system detection complexity and the system configuration complexity. Okay, this is the last part. As I have said, the detection of the composite multiple mode is very, very high, right? If we use the ML detection. So in order to reduce the ML detection complexity, I propose the lower complexity detection, which with using the conventional LLR algorithm. So this equation is the LLR value of the composite multiple mode. So this value means this value this value is the probability of each subcarrier is active or not. So in other words, if this value L is very large, that means this subcarrier is properly active, right? If the L is very less, right, nearly 0, that means this subcarrier will probably not be used. So by using this method, we can calculate all of the LLR values for all subcarriers, right? The eta means the index. The eta means the index of all subcarriers. Okay, here, right? By using this equation, yes.
Yes. Sorry to interrupt. Actually, we have only 10 more minutes. So
Okay.
yeah, so if you can finish it quickly so that we can take some couple of questions from the participants. Yeah.
Okay. Thank you. Okay, so
Thank you. Yeah.
yes. Okay, I will then quickly.
Maybe you can give your email address if any of the participants want to have further discussion. They can send some questions to you. Actually, yeah, to your email.
Okay. Thank you.
But there are already some questions from the participants in the chat box. Yeah.
Okay. Then
Yeah, just
let's go to the
complete it so
last
that
part.
I'll ask some questions. Yes.
Okay. This is the last part, right? And this is the suboptimal LLR detection of the performance compared to the ML algorithm, and the proposed the LLR algorithm nearly get the similar performance to the optimal ML detection, right? The performance loss is very huge, is very tiny, right? It's very less. It's not a big performance loss, but with very less detection complexity. Okay, this is the last slide, which is the limitations of composites multiple mode. So in our scheme, right, we didn't consider the transmit diversity, right? Because in the high SNR, the only the modulation base, the modulation symbol will be running detected, but the how to say? But the detection error comes from the modulation base. We have this effect, which means the BEP, right? The bit error probability for the PSK or QSK demodulation, which limits the diversity order of 1. So how to increase the transmit diversity? Maybe I nowadays I didn't find any good method. Maybe we can try if someone have the interest to try this topic. Maybe you can consider the coordinates interleaved, the composites multiple Ofdm or other Ofdm or other spectral modulation related scheme, right? The coordinated interleaved is one kind of famous. It's one kind of famous method to increase the transmit diversity. Okay, thank you. I have finished my talk. Sorry, my English is very poor, so it costs so much time, and I'm so sorry for that.
No problem, Julie. The talk was exceptional, actually. So you have touched upon many things, starting from conventional OFDM, and then you went on to OFDM with index modulation, and then multimode OFDM index modulation, and then finally you concluded with composite multimode OFDM index modulation. So it was a talk. If people are interested in this OFDM, then these are like advanced modulation schemes. So I think for many people it would be a very interesting talk to listen to what OFDM stores in place for the future communication systems, advanced OFDM modulation schemes. So there are some couple of questions from the participants. I will read out those questions. So,
okay.
Right. The first question is from Dr. Madhusudanan. So could you elaborate the concept of index modulation? Or in other words, like what is the difference between this conventional OFDM and spatial modulation and index modulation?
Okay. So I will go to the slides for the
difference between the spatial
right?
and index. Yes, that's right. Yeah.
Okay. So the question is about the difference between the OFDM index modulation and the conventional OFDM, right? That is right.
Yes. Yes, that's right. Yeah.
Okay. So the main difference between the Ofdm and Ofdm IM is that in the conventional Ofdm, all of the subcarriers will be activated, will be used for transmitting all modulated symbols, right? So in this figure, so in this example, the 16 subcarriers will be used for transmitting 16 modulation symbols. But in the OVDIM, only some parts of the subcarriers will be activated, and only the activated subcarriers will be used for transmitting the modulated symbols, which means the energy efficiency of the OVDIM is very high, right? This power, if in the conventional OVDIM, it needs much power to transmit all of these transmitted modulation symbols. But for OVDIM, it has maybe only half, right? If we consider this figure, it has only half power to transmit the modulated symbols. So the so the energy efficiency is higher than the conventional OVDM. And the other one is the BR performance, right? I have said in the high SNR region, the detection error only comes from the modulation, the modulated symbols. So
yes.
only detecting.
Yes, and the BR is very low, right?
Yeah, the
index.
BR is lower, and the energy efficiency is higher compared to the OVDM, the conventional OVDM.
Thank you, Dr. Junli. And one last question. So from Dr. Murthy. So when NOMA is superseding other techniques, why again go to OFDM? So
What?
it's a general question. So he's asking why we go again for OFDM. There is a advantage with NOMA. Like why again go to OFDM?
Sorry, I didn't understand your question. NOMA,
the question
right?
is like
NOMA, right?
Yeah, he's trying to compare NOMA is better than OFDM. He's asking the question. So why we need to go for again OFDM, like different kinds of OFDM modulation? Why not stick with NOMA? Yeah.
Okay. So actually the concepts of the OFDM and the NOMA is are different, right? The NOMA technique is mainly used for the multiple user systems, right? There are several the users are very how to say multiple user equipments. So different user will allocate the different power level, right? So and some user will have the high energy, some user will receive the lower energy. So I remember that there are some papers related to the compilation of OFDM and NOMA. Also, there are some papers related to the OFDM, IM, and NOMA.
Okay.
I mean, the concepts are different.
Okay, thank you.
Right?
Thank you. Yeah.
Yes.
So thank you, Dr. Junli. I think there are a couple of more questions, but there is no time. So I think thanks for your talk, Dr. Junli. So this was a exceptional talk on the advanced modulation scheme for future communication systems. So thank you again, Dr. Junli. Yeah.
Okay. Thank you. My English is very bad, so nowadays is not better, right?
No problem.
It's very hard to speak English, right? It's better to speak Chinese nowadays.
Yes, but anyway,
sorry
it was.
that.
Yeah, it was a good talk, Dr. Toli. Yes.
Sorry for that.
Oh.
Okay, so can I quit now, or?
Yes, you can leave. Yeah, thank you.
Okay, thank you. Okay, thank you.
So participants, I think, yeah, so we are running out of time, but just we'll take a 2 minutes break and then we'll start the next session. The speaker for the next session is Dr. Vaibhav. So we'll take a 2 minutes break and then we'll start the next session. Yeah. Dr. Vaibhav, are you here?
Hi, yes, I'm here. Can you hear me?
Yes, we can hear you.
Yeah.
So is it possible to turn on the video?
Yeah.
Yes, perfect. Okay. I just wanted to check like whether the video and microphone is working.
Yeah.
Okay. So we'll start the session in 2 minutes. Sorry for
No
the
problem,
last session.
Yeah, it happens. That's no problem. Yeah.
Okay. Thank you. Thanks for understanding. Yes, so welcome back, everyone. So I'm very happy to introduce Dr. Vaibhav to you all. So Dr. Vaibhav received the bachelor's degree in Electronics and Telecommunication Engineering from CSVTU, Billoi, India in 2012. The MTech degree in Electronics and Communication Engineering from LNM Institute, Jaipur, and PhD degree from University College Dublin, Ireland in 2020. So from 2012 to 2013, he worked as a lecturer with the Department of Biomedical Engineering, NIT, Raipur, India. From 2015 to 2016, he worked as a project associate in the project titled Mobile Broadband Service Support over Cognitive Radio Networks, funded by Media Labs Asia, Government of India. He was a visiting research student with IIT Delhi from Jan 2019 to May 2019 under the Erasmus Plus ICM research program. From September 2020 to December, he was working with Beijing Dublin International College as an adjunct lecturer. Since April 2020, he has been working as a postdoctoral research fellow with University College Dublin, Ireland. He is a recipient of the Best Paper Award at IEEE Globecom 2021. His research interest includes wireless communication theory, signal processing for wireless communications, integrated communications and sensing, and next generation multiple access techniques. So his talk will be on intelligent reflecting surface assisted wireless communications. So thank you, Dr. Vaibhav, for accepting our invitation to be part of our FDP program. Thank you very much. So you can deliver your talk now.
Yeah. Just putting this on. So can you see my screen properly? Yeah.
Yes, we can.
Thank you for inviting me. So I will be. I'll give a brief introduction about this intelligent reflecting surfaces, and people also call it RIS, which stands for reconfigurable intelligent surfaces. And we'll see how these surfaces can be used for the next generation communication systems. After the introduction, I will move towards some of my recent results. And the collaborations for that work, we collaborated with Professor Mark Flanagan and Professor Lee Nam Tran, both from University College Dublin, and Professor Rui Zhang from the National University of Singapore. So we will talk about a brief introduction about IRS and their application in wireless communication. We will look into what are the different sort of optimization problems in IRS assisted communications. Then we will shift our focus towards one particular problem on IRS assisted Mimo underlay spectrum sharing. We will discuss about one of the particular method that is having a very low complexity to solve that problem. We will discuss about some of the results then. So to start with, let's just consider a typical use case scenario where you consider this is a sort of a room or a house inside which we have an access point or a wireless router. And then there are different users which have different sort of like different quality of service or different applications they are or different goals that they try to achieve. So if you consider these blue beams, so user A and user D, so they have some objective, and that is just to optimize their quality of service. So maybe to have the best SNR, best SINR, or high data rate, or low error probability, or whatever sort of thing. So what happens is this router will create a path. It will, I mean, the waves that is being transmitted from here that will impinge on this wall and then get reflected similarly in here. Now, this is the best case scenario that these two users can get. If we see user B, that is the green one, it is kind of a swiped user. So it is having a wireless power transfer and at the same time maybe some information transfer. The same time user C wants to have a secure air path. So this is the red beam. This is the way we can create a secure path to user C, where it is like user E, which is an unauthorized user. So that user need to be blocked so that the information that is intended to user C cannot be decoded by user E. But what happens in the traditional wireless or the conventional wireless system is when these waves emerge out of the source. So at that point of time, like we do not have a control. It depends entirely on the antenna pattern, like the radiation pattern from the transmitter antenna. And if we have a very good directional antenna, so we can focus our beam towards a particular user, or if we have like many degrees of freedom, we can have like multi-beam sort of approach. But once the waves are like transmitted from the transmitter, then we have no control over the environment. It will entirely depend on like where are the buildings, where are like which is creating kind of a shadow environment, or it is kind of working like acting as a block in that path, or if my wave impinges on some wall. So depending on like the material it is made up of, some of the parts will be absorbed, some of the part will be reflected. Again, the reflection will occur based on the classical physics. So the thing is like we cannot control the environment, and that is not a very helpful thing. Like people have been trying to combat this uncontrolled wireless propagation environment for decades. So in the case of 6G, like, I mean, when we like 5G is being deployed in many parts of the world, even in India, I believe. So now people have started thinking like, what can we do for the next generation communication systems? Like when we have many users, and as like uh, the what we call is the information society, the mature information society. So now we are much kind of bothered about the security and privacy, and at the same time I like people nowadays are like watching live streaming videos, like high data rate communications with the limited amount of spectrum. So that is a challenge. So although like many different techniques specifically on physical layer are being suggested, and I believe like there have been many presentations in this FDP on the next generation like physical layer breakthroughs as far as wireless is concerned. This is another kind of a breakthrough advantage. where this paper came in 2016 that says a programmable metasurface with dynamic polarization, scattering, and focusing control. So this is basically people have developed some metamaterial tiles which can control the reflection angle. So this has like the waves that will impinge on the wall, like that will incident on the wall, and it will get reflected. So it is no more like the incidence angle is equal to reflection angle. We can basically create some time delay, which will create the phase shift in the in all of the waves that, and we will see how we can focus our beams towards a particular direction, or we can block the beam in a particular direction to deny the access to any particular user if you want. So what how these tiles actually looks like? So these surfaces are made up of many small tiles, and each of the tile is made up of, like, there are many meta surface meta atoms are there. So these are like the rough structure. We will not go into like how this electronics has been done, but I mean there are papers who explain it based on the like RLC circuits, like how to create the phase difference. Now, the idea of this whole tile is something like we will have multiple layers. In the front layer, we will have some electromagnetic functions which will basically do some absorbing and steering the beam. So it can absorb, like it can uh, like it will stop the reflection at all. It will completely absorb the beam, and it can steer the beam at the same time to any particular desired direction. We will have some switching configuration, and then we will have like on-off state, like these green surface, which each of the tile is basically will be connected to a gateway or a controller, what you can say, and this controller will decide that what to do, like whether to steer the beam in particular direction, whether to turn off the complete thing, or like turn on some of the elements to have to achieve some qualities, like to achieve some objective. So here is a typical simulation scenario to to justify like what is the benefit of using these hypersurface tiles. So what the idea of these hypersurface tile is that we can coat all of the, the inside the building. We can uh, put these tiles on top of the wall. So now the outer surface of the wall is not the sort of like bricks or cements or anything. It is basically the tiles. So on the left hand side figure, we have the traditional setting where this is a room which is partitioned into two, and here there is some gap, sort of like a door or anything. Now on the this right hand side of the, in the left hand side figure, the right half, we have a transmitter, this red thing, and there are multiple receivers on the left hand side room, and we try to see like what is the power that we get at each of these receivers. So you see like this yellow region is like when we have a higher power on this color bar, you can see, and the blue region is like where the receive power is very small. Why this happens is because when the waves are transmitted from here, so it gets reflected from maybe from this part. Some of the parts might be kind of uh, penetrating this wall and and being received in here, and most of the power is coming from the scattering through these traditional walls. Now if we coat all of these walls, inside of these walls, by reflecting surfaces, what happens in here is you see that now most of the region is in, like almost all the region on the left hand side room in the right side figure is yellow. So, and yellow is basically we are receiving a much higher power. So this is just a simulation scenario to show that how these reflecting surfaces can be helpful. So now people are uh, suggesting that what will happen in the next gen com systems when we will have these surfaces along with the traditional communication systems. So again, if you think of the use cases, so these surfaces, so each of the surfaces is made of multiple tiles, and we can put it into the places where we have a large crowd, a large number of users. So maybe in malls, or like where you can go for like small cells or like nano pico cells, that sort of a scenario. In a like now it is still like this research is in very immature state for now. So people are thinking like whether to put all the risks at the same place, or should we go for like distributed risk sort of a distributed IRS sort of a configuration, or like should if I am placing an IRS at some place, so should we turn on all the tiles, or in order to save some power, can we turn off some of the tiles, and what is the optimal configuration? And also there are like many uh, open areas of research into that. At the same time, we can put it on, if you go on a highway and you see a big advertisement board, so we can make that advertisement board out of these IRSs, where in specifically in the area where the connectivity is not that good. Specifically, if you go into the millimeter waves, so over there, as we know that the propagation characteristic is not very good. The power loss is very high in that uh, in that uh, frequency bands, but we have a large chunk of spectrum that is unused over there. So we can have the broadband services over there, and we will get very high capacity. The problem is that their propagation characteristic is not good, and we can put these IRSs in there to act some sort of passive relays, or even like people are talking about like active IRSs nowadays. So this is the motivation of using the IRS for next generation communication system. And now we will see like if we use this IRS to design my communication system. So obviously, since this IRS is made up of multiple tiles, and each of the tile is basically can provide a particular phase shift, but now all of them are working in a collaborative fashion. So it is an optimization problem, that how do we like what is the optimal phase shift of each of the reflecting tile. So if you see on a broader level, like we will have these four types of optimization problem in that. So now here we consider that my transmitter is a multi-antenna transmitter, and I have an IRS, and I don't care about like, I mean, what happens at the receiver for the time being, be it a multi-antenna or a single antenna receiver. But the major focus in here is if we want to do the transmit beamforming, that is an optimization problem, or that is like transmit beamformer is my optimization variable. And at the same time, I want to do my IRS phase shift, like to optimize my IRS phase shifts. So that is another set of optimization variable. So if you see the channels, as we will see in some next of some slides, so because of the channels that is from transmitter to IRS and IRS to receiver, there exists a inherent sort of a coupling between this uh, transmit beamformer W and the IRS phase shift vector theta. So in the first type of optimization problem, we have this transmit beamformer and IRS phase shift are coupled in the objective of the optimization problem, but they are independent in the constraint. So an example of this is if I want to maximize the rate in my say Mimo com system, but at the constraint, I do not have any quality of service constraint. Like I want to like maintain a minimum rate or a minimum SINR at any of the particular user. If my goal is just to maximize the rate or the sum rate, then in the objective we will have coupling between the optimization variable. In the constraint, we will have no coupling. Second type of optimization problem that we will see in IRS assisted COM is we have only the transmit beamformer in the objective, but transmit beamformer and IRS phase shift are coupled in the constraint. So an example of this is if I want to minimize the transmit power of my overall system, like from the transmitter, And at the same time, I have some SINR constraint, like, or the quality of service constraint the at the receivers. The third type of problem is when only this IRS phase shift or the theta vector exists in the objective and W and theta are coupled in the constraint. So an example of this is when I try to minimize the IRS energy consumption in a multi-IRS setting with the SINR constraint. And the fourth one is when we have the coupling between these two optimization variables, W and theta, both in objective and the constraint as well. An example of this is rate maximization in Mimo interfering broadcast channel. So now why we are talking about this coupling is when coupling exists between the optimization variables, if they are multiplied together, something sort of that sort of a scenario occurs. Solving those optimization problem is challenging in general. So in this talk, like in the rest of the talk, we will be mostly focusing on the fourth type of problem, and that is, I can say, is the most difficult one because we have coupling in both objective and the constraint as well. So what people normally do to solve these sort of like, or to design this sort of a system in literature, what we see is they use alternating optimization most of the time, almost like all of the time. And so the idea behind alternating optimization is if I have to optimize two variables, W and theta, so I start my iteration with some initial values of W naught, theta naught. I fix my theta naught and try to optimize my transfer beamformer W. Once that is maximized, then I fix that particular W and try to optimize theta. And we do it repetitively in an alternating fashion. So that is called like the basic idea behind alternating optimization. It is not new, like being used for like many decades. But the problem is that since there is a coupling between them, so even when we are talking about the local optimality, we are not guaranteed that we will hit the local optima, because like if I fix the one set of optimization variable and I'm only in a particular iteration, if I'm only trying to optimize the other set of variables, like it is hard to prove that we hit the local optima. And specifically in some scenarios, like when my overall the optimization problem is highly non-convex, then it like the performance becomes like even worse in that scenario. So basically we will be focusing on the problem where we have the coupling between these optimization variable both in the objective and the constraint as well. So that comes to the part of IRS assisted MIMO underlay spectrum sharing. So consider this scenario where I have so I'll just give a brief introduction of this. The idea of a spectrum sharing is that like you know that when a particular service provider is it uses a spectrum, he has to buy the license for that spectrum. But there are scenarios like that particular service provider or its user are not using its spectrum all the time, or even if it is using. So basically in like there are many uh, uh, paradigms of sharing the spectrum. But what we do is, can we deploy an unlicensed network near to the licensed network such that unlicensed network will also use the same set of like same frequency band for which the licensee is the primary network. But what we'll do, like if we use the same spectrum, we will basically be creating interference to the licensed user. But can we keep our interference below a certain threshold that the quality of service of the licensed receivers is not degraded beyond a particular limit? That is the idea of underlay spectrum sharing. There are other aspects like overlay and interweave and yeah, and maybe like some mixed strategies and all. So here we are focusing on the underlay spectrum sharing. So basically this red sort of a region, that is the primary coverage. That primary network holds the license to use a particular band. Now this green sort of a region, that is the secondary network, secondary coverage. This secondary do not have to have the license to use, but it is still using, provided that the interference it is creating on this primary receivers is always and always below a certain threshold, so that their quality of service is not compromised too much. So here we have the transmitters, ST, that is secondary transmitter. It is a multi-antenna node. We have, say, one secondary receiver in here. We will see how this work can be extended to multiple secondary receivers. So we have one secondary receiver. This is again a multi-antenna terminal. We have this reflecting surface that is made up of, if you can see, these dark blue dots. So these are different tiles. That can be like many tiles, like maybe in the order of hundreds or thousands for that matter. So if you see, like, we have a direct link from transmitter to receiver, and we have a reflected link that goes from transmitter to surface and surface to receiver. And the same thing happens for the primary receiver or the licensed receivers. Now, we try to formulate the problem. So the signal that is received at the secondary receiver, so X is the information that is being transmitted from the secondary transmitter. HTR, this is the direct link from secondary transmitter to secondary receiver. Now here is the link that is reflected from the IRS. So TI is the channel from transmitter to IRS. This theta is a diagonal phase shift vector that each of the tiles at the IRS is providing, and HIR is the channel from surface to secondary receiver. So now we try to maximize the rate at the secondary receiver. So since this is a Mimo configuration, so it is a standard log rate formula for the rate, and we try to maximize that rate. Now, if you see, that rate depends on two things. One is this theta and one is this X. Now, this X is basically my transmit beamforming vector, and here we basically deal with transmit covariance matrix rather than the beamforming vector. And this theta is the phase shift of, like, if I consider at the IRS, I am having n sub I number of tiles. So this is basically a vector which is having ni elements. And now there are many models, like how do we model this phase shift at the IRS? But the most popular one is that this is basically like the phase shift that is being provided is basically on the unit complex circle. So we model it as e raised to the power j phi, where phi is the phase shift that it provides, the angle of that. So we try to maximize the rate. Now we have some constraint. The constraint is that we have a certain transmit power budget. Each of, like, modulus of each of the phase shift that is being provided should be 1, because it is lying on the complex unit circle. And in 2C, this is the interference constraint at the primary receivers or the licensed receiver. So the interference that we are creating should be less than or equal to a predefined threshold pk for each of the k primary receivers. So now if you see the coupling, between, so I have two optimization variables in here, capital X and theta. X is a matrix, theta is a vector. So the coupling is in the objective in form of ZR. If you see, ZR is basically is a function of theta, if you see at the bottom, and it is being multiplied with X. So somehow there is a multiplication between theta and X. So they are coupled together. The optimization variables are coupled together. And another coupling is in 2C, where we have this ZK. Again, the same thing. It is Z is a function of theta, and X is my transmit covariance matrix, which is an optimization variable. So now these two things are coupled together. The traditional way to solve it is I fix my theta with some, like, I start with a feasible theta. I try to, once you fix the theta, so now this is conventional, like, Mimo rate optimization problem under interference constraint that has been solved like many times. And for the next time, once I have an updated X, I fix that X and try to optimize my theta. Again, that is like, that can be done easily, not a big deal. But the problem so we will see, like, what is the existing method to solve this. So the existing approach, So these are pretty recent paper in 2020, 2021. So in the first paper, they considered a single secondary transmitter, multiple secondary receiver, and a single primary receiver. All the nodes are multi-antenna, and there is one IRS. So they do the weighted sum rate maximization problem, where they convert that WSR problem to WMMSC weighted MMSC problem, and then used alternating optimization with CVX. In the second paper, they had this all the same configuration, but in place of one primary receiver or one licensed receiver, they had multiple licensed receiver, followed the exact same approach with a little bit of like variation. Again, they do that, convert that WSR problem to WMMSC, use the AO, and then use the CVX. We will see in detail how they do this. But what we see that their performance is bad when the coupling between these optimization variable X and theta is strong. And what I mean by strong is, if you see in here that normally if we try to solve a Mimo rate maximization problem when we don't have an IRS or anything. So in that case, like we don't have an IRS, and at the same time, suppose we don't have like a spectrum sharing, like it's a licensed point-to-point Mimo rate maximization problem. So what happens in that case is, even if we have this kind of a convex constraint that the rate that I am transmitting, so sorry, the power that at which I am transmitting is less than equal to k. When you solve the problem, you see this is binding. So that means we will transmit at full power. That makes sense. Like if I transmit at a higher power, I get a better rate. So if I'm trying to maximize the rate, it makes sense to transmit at full power. But in here, we have another constraint. So what happens, like if I transmit at full power, I may be violating my interference constraint at the primary receiver. So these two constraints, so when you solve the Mimo rate maximization problem in an underlay spectrum sharing setting, or what we call is Mimo interfering broadcast channel, what you see is like if you plot rate versus transmit power budget, so that curve increases and then it saturates for the larger value of Pmax or the transmit power budget. Why that happens is, even if I am having like more power to transmit, I cannot, because if I transmit at a higher power, I will violate the interference constraint. I will be creating more interference at the primary receiver or the licensed receiver. So the curve flattens out. So now in that region, I will say, like when IRS comes into picture, when we have a larger Pmax, the coupling between X and theta becomes very strong, because now again we reach a kind of a rate saturation region where even if I am having more power to transmit, I cannot, because I don't have the license. I have to follow like what my licensed network is saying, like, oh, don't create more interference at my receivers. So we will see how they deal with this in the existing approaches. So we will consider this first, the scenario in the first paper, where they have single secondary transmitter, multiple secondary receiver, one PR, and all multi-antenna nodes. So they try to maximize the rate. Sorry, this is the case of one secondary receiver and one primary receiver. So in this case, okay, I try to maximize the rate. I have some transmit power constraint, interference power constraint, and unit modulus constraint at the IRS. So what they do is they assume that the symbol that we are transmitting is X, that is WS. W is my beamformer, S is my information. And then they apply some linear decoding matrix at the receiver to estimate what is S. So S hat is the estimate of S at the receiver. So this U dagger is my decoding matrix. For U is the decoding matrix. You do the Hermitian at the receiver. So the idea is like there is a relation between rate and like I mean the achievable rate, or what you call the capacity, and the bit error rate or symbol error rate. So if I minimize my bit error rate probability, I can maximize the rate. So what the idea in here is, to maximize the rate, I need to minimize the difference between the transmitted vector S and the decoded vector S hat. So this is the mean square error. And then they use some auxiliary matrix V, and they kind of formulate this problem in 3 into the problem in 4a, and then they start using the alternating optimization. So converting that rate maximization problem into error minimization problem, and then again that error minimization problem into maximizing this function h, that is very popular. So this was published in 2011, you see at the footnote. So this says an iteratively weighted MMSE approach to distributed sum utility maximization for MIMO interfering broadcast channels. So although, like, I mean, for a point-to-point MIMO, this has been done earlier, but for when you have like interference constraint in there, so this was done in 2011 in this DSP paper. So after formulating 4, they try to optimization W for all of the fixed things. So here we have like V, U, and theta, they are all fixed. So the problem becomes 5, and that is a convex optimization problem. You can solve it using CVX. But although we have fixed theta, you see in ZI, in the transmit power, in the interference constraint 5C, there is a coupling between W and theta. But although, like, I mean, theta is fixed, so the solver thinks at this as like I have only one optimization variable W to optimize. And in the next step, they fix V, U, and W, and they try to optimize theta. That is in here. Now again, this is still non-convex because of constraint 6C. So they relax this constraint and then use the semi-definite programming to solve this. And then, so basically they create, theta is a vector, they create a matrix using the outer product. And from that matrix, they try to extract the unit, like, I mean, they try to create, convert that matrix that may be of higher rank into a rank 1 matrix, and then extract the theta. So and the optimize, like, once you optimize W, you optimize theta, this now V and U can be done in closed form. So that is given in that paper. And yeah, so this is how they repetitively keep doing this, optimizing W and theta, like fixing one and optimizing the other. Now, like, again in here, if you see this B double dot and G double dot, I have not written in here, but they are basically the function of, again, W and theta. The coupling is still there in the objective as well as the constraint. Another problem with this sort of approach is SDP is, although it is like very frequently used, very standard, very powerful tool for this sort of a problem, but the complexity is extremely high. And another problem is when you do this Gaussian randomization, you are not guaranteed to hit the local minima, and we don't know when to stop. Like normally what happens, like if the change in my objective function, when I'm doing the iteration and my objective is kind of not changing with iteration, we think that it has converged. But what happens in case of Gaussian randomization is, because I'm randomly generating the vectors, I'm not sure, maybe if I do 5 more iterations, maybe I hit a good Gaussian random vector and my objective may change. So it is really difficult to say that when my, like, are we really converged or not? So 2 problems, high complexity, and it is difficult to prove, like, is this the best local optima that we can get? So because of these shortcomings, what we propose in here is something called penalty-based dual decomposition method. So what we do is basically, if we go back again into in this main problem in 2, so I want to maximize my rate. I have transmit power constraint, interference constraint, and unit modulus constraint. Coupling is there in the objective 2A and in 2C. So the idea behind this penalty-based optimization schemes, they are like very, very popular. They convert a constrained optimization problem into an unconstrained one. So what they do is they, like, theoretically we can, or we say, like, if we have an objective, we have a constraint. So what they do is they multiply the constraint with a penalty parameter and take it into the objective. So now my problem becomes an unconstrained one, and if I try to maximize, my original objective. So if my original objective is say fx, and I have done some fx minus some c times gx, if my goal was to maximize fx, so obviously that penalty term like c times gx should be 0 at the convergence theoretically. So like there we need to do some regularization into that, but the basic idea is to convert the constraint optimization problem into the unconstrained one. Now here what we do is we do not take all of these constraints into the objective. We only take the constraint that is most challenging, that is 2c, where the coupling is there. We take that constraint back into the objective, and now we remove this constraint from here. So what happens doing the good thing with that is now we have coupling between the variables only in the objective, and all of my constraints are decoupled now. So now again, since we will still be using alternating optimization, but I hope that we hit a better I mean we hope that we hit the local optima, because, or at least my converge point will be better than the existing scenario where they apply this alternating optimization, but they have coupling in multiple places. So because of that, like in a non-convex problem, it is really difficult to hope that you really hit the local optimum. And we will see like why we do not take constraint 2b and 2c in 2d into the objective function. So what we basically do is we use this penalty dual decomposition method to deal with the interference power constraint IPCs, which was basically 2c. So we define a function that is like this trace of this function, that is my actual interference that I am creating at the license receiver. That should be less than equal to pk. So if I add some small number sk, so that will become equal to pk, and then I subtract this pk from that. So this whole thing basically my gk is equal to 0 basically. So if you see in here, so this log det function is the rate of my secondary receiver, and at the same time we have this gk function with first order. So this is basically my Lagrange function, and here is my penalty. So this is the first part in here is sort of a Lagrange multiplier, and 1/2 rho is my penalty parameter with the second order correction term. So if you see this paper that appeared in 2020, so they say like penalty dual decomposition for non-smooth non-convex optimization. So this they say that this penalty dual decomposition method that they propose is basically like it's a combination of like this Lagrange multiplier methods, penalty methods, and then you see this BCD block coordinate descent and gradient projection. So they have combined all if you go deep into the theory, but the overall idea is from the objective we subtract a Lagrange thing and we subtract a second order thing with penalty parameter. If you see why we have this 1/2, so there is no need to do this. Only thing is like if we take the gradient of this gk square, so that 2 will come in front and that 2 will cancel with this 2 in the denominator. It will look nice. That's the only idea. You can neglect this 2 if you want, no problem into that. So this epsilon k's in here are the Lagrange multiplier, rho is the penalty parameter. So in that case, my objective becomes r hat, which is r hat is the function that we have just seen in here. And we have a series of vectors, so sk, and since we have k such constraints, so all of those we stack in a vector. So s greater than 0, and then we have this transmit power constraint 2b and unit modulus constraint 2d. Now we can see that this in 7b, since this is a slack variable or an auxiliary variable, 2b and 2d, they are like this 2b is only a function of x, 2d is only the function of theta. So the constraints are now decoupled. I only need to worry about the coupling between the constraint and the objective. So next step, we define some feasible set. So this set X is the feasible set for my transmit covariance matrix. and theta is the feasible set for my IRS patients. So now it is very simple to solve this optimization problem. So what we do is we take the gradient of my objective function r hat with respect to theta. Now, another point in here is this r hat is also a function of epsilon and rho, which are basically in here. Epsilon is the vector for Lagrange multipliers. Rho is the penalty parameter. We will see how what is the meaning of those in later figure. So we take the gradient with respect to theta, and we also do a projection step. So if my theta is not in the feasible set that we have just defined, so the only condition in this feasible set is each of the elements should be unit modulus. So if it is not on that unit circle, we simply scale it. So that is the scaling operation happening in 11. And if the modulus of any of the theta is 0, in that case, we randomly choose the phase for e raised to the power j phi, and that already have a unit modulus. Okay, and then we do the similar thing for my transmit covariance matrix. So we take the gradient with respect to x for this r hat that is given in 12. Now the projection onto the feasible set x is basically a water filling problem. So since it is very well known, we can do this with the projection onto simplex. So that is what I have explained in here. I won't go into detail. I believe like you know this, like you just need to do the eigenvalue decomposition and put your like the powers on your dominant eigen modes there. So this is the problem. Sorry, this is the solution to like 15 is the solution to your projection onto the feasible set of x, which is basically the water filling solution. And once we have updated my theta, updated my x, I have I have to update this s, which was introduced in here in this function when we define gk. So this s, it is known that this should not be negative. So we just do a maximum of 0 and pk minus trace. So this ensures that I'm not creating interference at the primary receiver higher than what we are allowed to. So now here is the basic gradient projection algorithm, what we do in there. So this algorithm is for fixed epsilon and rho. So we input theta naught, start with a feasible theta or a random theta, some random transmit covariance matrix as S naught, epsilon, mu naught. Mu naught is the step size, alpha naught is step size, and rho is my penalty parameter. So what we do is we take the gradient in here in line 3. You see, we take the gradient with respect to theta for r hat, multiply with step size, and add to the previous theta. Once we are done with that, we project it onto the feasible set theta. We do the same step with a different step size and project it onto the feasible set of x. Then we update my all of the s elements in the s vector. And once we are done with that, since zk is a function of theta, so we update like all the channels. All the channels are the function of theta, so we update the channels and we repeat it. We keep doing this until we have the convergence. And then since this has done for the fixed Lagrange multipliers and fixed penalty parameter, now we go to algorithm 2, which says like now we give these inputs here. Kappa is a constant number that is less than 1. Now what we do is we repeat, we solve the problem using algorithm 1, and once we had the convergence, then we update my Lagrange multiplier and the penalty parameter like this in 4 and 5, and then we repeat the whole process until we have the final convergence. So we will see like how this looks like and how what is the meaning of like changing this Lagrange multiplier and penalty parameter later on. Now the same thing can be this approach can be extended to the case of multiple secondary receivers. So in that case, we can formulate a weighted sum rate or a sum rate maximization problem in here. So I have like this L is the set of like capital L is the total number of secondary receiver, and L is the set that contains the indices of all of them. So we try to maximize the sum rate. Now we have like, since we, in this case, we have to do multiple transmit beamformers. So like the trace of all of the transmit covariance matrices should be less than pk. Similarly, this overall interference power at each of the primary receiver less than pk, and this 17D is exactly similar to the previous one. So what we do is, again, we formulate augmented objective by taking 17C into the objective function, and then the we keep 17B and 17D like as it was in the previous case. Projection onto 17D is exactly similar, like it is just a scaling operation, and projection for 17B, you know, for this all of these XLs. So what we need to do is just stack all of these transmit beamformer next to each other, do the same water filling, it will give you the same solution. So the exact same algorithm can be applied for the case of multiple secondary receivers. Here we did the complexity analysis. I won't go into the detail, but I just go to the practical scenarios. So it like the papers that are coming out, they say like, in order to these IRSs to be effective, the number of tiles in the IRS will be of the order of hundreds, or maybe some papers say thousands. That is obviously much larger than the number of transmit antennas or number of receive antennas at any of the nodes. So that's why we take this assumption that the number of Ni is the number of tiles, that is very, very greater than number of transmit antennas at ST, number of antennas at secondary receiver, and number of antennas at the primary receiver. So in that case, for the benchmark scheme like that WMSE approach that I already discussed, their approximated complexity grows with a third power of Ni. So now you imagine if I have like 256 tiles, or like maybe 1,000 of tiles, an algorithm growing to the third power of that is not so charming. It is difficult, like to solve. It will take a lot of time to solve. But the complexity analysis, what I presented here, if you see the complexity of our algorithm, that grows linearly with Ni, and that is the best you can get in that, like in these sort of like an iris systems. You can't go below that linear, like you can't get like log or something in that. So this is like really this algorithm is really good when you have a larger scale system. Here are some simulation parameters, and I will go to the results. So this is the result for one set of channel, where I show like how this rate changes with the iteration. So you see this black line. So let us consider the NT equal to 4. So we have 4 transmit antennas. That case, I'm transmitting at 20 dBm. So what happens when I fix my rho equal to 10? So this dotted line, if you see, that is my augmented objective, which is guaranteed to be non-decreasing. So that grows up, and it becomes like kind of converge. It becomes constant, no change into that. If we hit that region, then what we do is we update my the penalty parameter, this rho. So from 10 to 1. In that case, now you see this dip. So basically this line is not there. It's just like connected the dots. But what happens in that case, like it starts from this place, and again, it converges to some point, and we keep doing this until the difference between the dotted line and the solid line is less than like some, I think in here we set like 10 raised to the power minus 5 or something. So that is how we say like my algorithm has converged. And in this region, if you what you will see that in all of these regions, any of my constraint, maybe it's like the transmit power constraint or the interference power constraint, they were not satisfied. So basically I was into a non-feasible region in all the black and red ones. And then in here we have satisfied all the constraints. And in that case, what happens that the penalty part, like the Lagrangian multiplier and the Lagrangian part and the second order part, they both goes to 0, and these like the augmented objective and the true objective, they both becomes equal to each other. We stop in there. So here is a result for, so this BCD IAM is the first paper, WMMSC is the second paper that I was discussing, that they use this the WMSC approach. So what you see in, when we have a smaller transmit power budget, all of the algorithm, the blue one is the proposed method, all of them are performing very similar. When we have the value of Pmax, like the maximum transmit power budget increases, our algorithm starts performing better. So this is the region where I say the coupling between the variables, the optimization variables X and theta, is very strong. In this region, although, so this flattening thing will happen even for the blue curve, maybe in when we have even a larger value of Pmax. So what happens in here is, although we have some power like left, like we can transmit at a higher power, I cannot satisfy the interference constraint. So since they do a suboptimal theta and a suboptimal X, or a really suboptimal, I would say, so that's why they are saturating at in a much smaller value of Pmax. We are we are finding a better X and theta, and within that uh, the feasible region, and that's why our curves keeps growing on. I don't know whether this is the global optimal or not, but it is certainly a better local optima than what we see in the blue and the red curve. Here is the result for the proposed this penalty based algorithm when I increase the number of risk elements. So we start from 2 risk elements, we go till 2 raised to the power 8. And so what happens is, like, if I'm exponentially increasing my number of tiles at the wrist, my rate is growing exponentially, and maybe again, you know, it may saturate at some point. We don't know like when. And this is the figure when we have multiple secondary receivers. So the previous figures were when we had single secondary receivers. Now, as we said, like the work can be extended to multiple SR using the same analogy. So here we just compare, and we compare with the second existing paper, which used the WMMSC, because only that in that paper they used uh, multiple secondary receivers. So then in that case, now in here what we see is, even for the small values of Pmax, their performance in the WMSC approach is inferior. Again, this happens only and only because you have coupling at multiple places, and now as your optimization problem is more involved, like because you have to design if you have 2 secondary receiver, you have to design 2 independent beamformers. You have to so, and both of them are coupled together with the IRS phase shift. So your coupling is even more stronger in that scenario. So even for small values of Pmax, performance becomes very inferior if you approach via WMSC solution. So this is the end of the presentation. So to conclude, we considered the rate optimization problem for IRS Mimo underlay spectrum sharing system. In literature, this, like, you can also say this as IRS assisted Mimo interference broadcast channel. We proposed a penalty dual decomposition based gradient projection algorithm to jointly optimize the transmit beamforming and IRS phase shifts. So the performance has been shown to be superior with much lower complexity, which is like the complexity is linear, which is the best you can get into this sort of a system. And that is the end of the talk. If you have any questions, please go ahead.
Yes, Dr. Vaibhav, thank you very much for the exceptional talk. So we have a couple of questions.
Yeah.
Not exactly related to the optimization problem, but in general. So yeah. So is this intelligent reflecting surfaces, or maybe like a couple of, or like many multiple IRS elements, can it replace the conventional relay for the future communication systems?
Yes, it can, because if you think of conventional relays, so there are like the basic configurations are like amplify forward, decode forward, or like how to say incremental relaying and that sort of a thing. So now the work that I have presented is for the passive one, so it can only reflect your signals. Now there are people are talking about active rays, which can like multiple, which can reflect as well as refract, and at the same time it can also embed its own information if if it has some information to do. So now the thing is, since we have multiple tiles which are doing some function in a collaborative fashion, so I believe it can replace the relays now. But the thing is, it what is the cost of deploying the thing? So relays are like not that expensive, since these are like hyper materials like meta surfaces and meta materials and all. So it will depend how much power it is consuming to do all of those things, to activate all of these tiles. How much signal processing, how much time we spend to optimize all these tiles, and what is the cost of, like, how much money you have to pay to buy that thing. That will be the, so I won't say like in all of the scenarios you can replace the relays. Like some places using relay is a might be a better, a clever choice, I would say.
Okay. Thank you. And another question from the same participant. So is this environmental changes affect the IRS elements, or it will show constant performance in all scenarios? Because sometimes these IRS elements must be outdoor, right? Not all the times it must be indoor. So it must be outdoor in different scenarios. So at that point of time, like what will happen? Like if there is some rain, or like if there is some cloud or fog.
Yeah, so that will be reflected. So basically the controller needs to know about the channel, like what is happening in the channel. So if the channel is bad, so obviously, I mean, the job of this IRS is only to provide the phase shift. Now what happens after it has provided the phase shift, what happens to the wave when it is traveling through the channel, IRS has nothing to do with it. If that information has been fed back to the IRS that, okay, the channel is not good now, this, like, the channel has changed, so obviously that information will go to the controller or to the base station, and the base, either the controller or a server will do the based on the new channel condition, it will again try to optimize the phase shifts. So it will be a, I think you need to update your phase shifts within your coherence interval. So the channel has changed, you again go back, solve the optimization problem, and tell the controller that this is the best phase shift that you need to do now.
Right. So based on the channel conditions, it needs to change.
Yeah. Every time. Yeah.
Right. And one more question is, like, the optimization problem that you presented. So it was with considering the channel state information is perfect, or maybe like it's known at the transmitter as well as the receiver. So what happens, like the performance of IRS if the channel state information is imperfect or unknown?
Yes, there are like so the thing is, now when people compare like whether putting these IRS is better than a non-IRS system or not. So there are multiple papers who do robust beamforming, or at the same time like robust this IRS phase shift, we call it like reflect beamforming. So if you have imperfect channels or completely no channels, and when you do the optimization, you compare that with the no IRS case. So IRS has been shown to be always better than that. So IRS still shows that the advantage, but I mean, now it depends. Like, if you try to really make that reflected link very, very, very noisy. So that I have not, like, particularly I have not simulated or tried that thing, or read that paper. Like if I'm writing the paper, I won't consider a scenario that that link is very poor and IRS is not performing good. Yeah, but if you see, like, there are multiple papers, and even for no CSI or partial CSI case, IRS is still performing better than the no IRS case.
Okay. So thank you, Dr. Vaibhav. Over to Dr. Inverson. Just a moment.
Thank you, Dr. Vaibhav. It was very wonderful talk, and you touched upon several different aspects of wireless communications. Now we'll see if there are any questions from the participants. If not, probably we can conclude the session. Are there any questions from the participants? All right, it looks like there are not many questions from the participants. Right. Thank you once again, Dr. Vaibhav, for your talk and accepting our invitation. I'll nice meeting you after so long time.
Yeah, thank you. It's really nice to see you after a long time. So I think things are better at your end. It's good.
Yes.
Thank you. Yeah.
All right. Yeah. So since there are no questions, we can end the session. Thank you, Dr. Vaibhav, and have a great evening.
Thank you for inviting me.
So to the
Bye.
participants, thanks again for spending your valuable time, and the certificate will be issued to you by the registered email. And if you have any questions,
The feedback form.
Feedback form will also be shared with you through the registered email. And if you have any questions, in relation to or if you misspelled your name or anything, you can contact us either through the same email that we will be sending, or you can you might have our convenience email ID. Probably you can give us a call, or you can write us an email. We'll be able to better resolve it. All right. Yeah. Feedback form as well as the certificate will be shared with the same email. And thanks once again for spending 5 days with us here. And I hope the session was very useful to you. And if you have any questions, in relation to contacting either one of these, speakers, or if you wanted to contact us as a conveners here, we are more than happy to, accommodate all your requests. Therefore, please feel free to contact us. And in feedback form, please mention what went good and what went wrong. We'll be able to rectify that in upcoming FDPs. Right. Thank you again, and on behalf of the the Department of EC, I would like to thank my colleague Dr. Sunil Chandra, Dr. Sadish Tiwari for their efforts they spent here to conduct this Friday FTP. And thanks for the organizers and the participants again, and ITKM and all of the supporting supporting staffs from our end. And thanks once again for all the participants. We can probably get the call if you have no questions, or if you have any other comments, you can let us know quickly. We probably will be able to take some general questions in terms of feedback or any certificate. You can type us that here. We'll be able to answer the questions. If not, then we can end the call. Yeah, so the YouTube links, you'll be able to access that through, if you go to the SRMAP YouTube channel, you'll be able to access it. If not, then, while sending us the feedback form, we will be probably sending you the YouTube links as well, all the 5 days YouTube links to you. But, it should be available online anyway. You can just log into YouTube and you can see from SRM University AP web page, YouTube page. Any other questions? All right. Thank you, and have a great evening. Bye.